All right, guys, we're going on to the next chapter, next unit, which is about files, reading from files, writing to files. Pretty important stuff. You know, without files, what happens? Everything you type into the computer, every time you turn it off, it's all gone, right? That's why you always do file save after you've gotten some work. But so far, our programs have not been saving anything to files. But before we do that, I just want to touch upon a couple of kind of cool things in idle that we might take advantage of later. And so specifically, I want to show you, you can use the plus sign to add things. I'm just in a Python shell. I didn't make a new program, right? You can use multiplication, the star to multiply things. But you can also use the star to do something a little bit different. What if you put a word there in front of the star? All right, that seems silly, right? But what if you wanted to print a line, say, of asterisks? There's our asterisk, but we want 80 of them, or 60 of them, or 40 of them. That's kind of nice, right? Because we might have some program that needs to generate that number of asterisks. And I think we did a dice program that printed out the relative frequency of the number of rolls, like you rolled a 7 and you roll it, whatever. We may have used a loop to print out the asterisks, but this would have been a much faster way. We have recently been taking advantage of that to create our array, right? Array is equal to, and I need 10 empty numbers, right? And then so when I printed out my array, I had an array of 10 empty numbers. So the multiply can do math, but it can also allocate, if it's not a number that it's multiplying by, it'll do something else. It'll repeat whatever that was, the specified number of times. So we're going to make a little teeny tiny program that will make it a little teeny tiny bar graph based on the array. So let's just do some nums. And it doesn't have to be a very long list, but type in a whole bunch of nums between like 10 and 50, something like that. Just make them up. Doesn't matter. Doesn't have to be my nums. I said 10 and 50, and I already threw in a 65. It doesn't matter what the numbers are. Okay, right. That's our data. Now we're going to print it out. For the value in nums, print that value. But that's boring, right? Just a series of numbers. Our brains don't process a series of numbers very well. That's why we love graphs. So we're going to draw a graph. Same syntax. For v in nums, print that num, print that value, print that v, but also print out that many asterisks. V times asterisk. You don't like asterisks, you could make that a hash symbol. You like dollar signs because we're earning lots of money here? You make dollar signs. I'm going to go with asterisks. And I'm going to space it out a little bit to make it a little bit easier to read. That's a star, and I put a star there, but like I said, that could be anything. All right, now when we run it, we'll have our pretty bar graph. And there it is, right? Here's the numbers with no graph attached. If you made up different numbers, yours will look different. And here's the numbers in the form of a bar graph. Making a vertical one would be much more challenging. We could do it though, but we wouldn't do it with a simple loop like that that's printing out asterisks, right? Because how do you print from top to bottom? That would be a little bit of a challenge. So instead, we'd probably use turtle code to draw a bar graph. What would that look like? Say we wanted to use a turtle to draw. And I know that if I write on the board, you'll be able to see it, but I'm going to lift this up just so that people can see this without the screen in the way. Not that there's that many people on that side of the room. But if you want to draw a bar graph, you'd pick a different pen. If you want to draw a bar graph with the turtle, right? We know how the turtle works. You turn left 90 degrees. You draw a certain distance. And then you turn right 90 degrees. And you draw a little distance, which would be like W for width. And then you go back down the same distance. Let's make this H for height, right? And then, so that was a right 90-degree turn. That was a right 90-degree turn. You come down here, and you make a left 90-degree turn there. And maybe you go a little bit ways, like that. So that's how we would draw a bar graph. You would do all of this for one number. And you would do it again for another number. And another number, you'd repeat this. The fact that it's being repeated makes it sound like this might be a good function. You'd certainly at least put it in a for loop. I think we ought to go ahead and do that too while the iron is hot on the idea of using arrays to hold, numeric data, a bar graph of data. So I'm going to need to memorize left 90, right 90, right 90, left 90. Hopefully I can. Why don't we just take note of that in a little notepad? Help my little brain keep track of it. Okay, so turtle bar graph. I'm probably going to draw a short distance, which I'm going to call the spacer, right? Draw a spacer. Then I'm going to turn left. Then I'm going to go up the height of the bar graph. So forward the height. I've gone all the way up, and then I'm going to turn right. I'm going to go forward the width of the bar. And I'm going to turn right again. And now I've got to go back down. So again, I have to go to the height of the bar. No. Forward the height of the bar. And now I'm down at the bottom. So I'm going to want to turn left again and be ready for the next part of the graph. So that's a left turn, turn left, and draw the spacer. Or at least half the spacer, right? We'll see what it looks like, and maybe we'll make some modifications. But that's what we want our turtle bar graph to look like. All right, y'all guys who walked in, you're going to need to type in just a little bit of code that we've already covered, which is this stuff. Just those 3 lines of code. All right, so we're going to import our turtle class. What are we going to name our turtle? Leo, or Leonardo. Okay. Is equal to turtle dot capital T, turtle. And don't forget the parentheses. All right, let's get this part going without making it a function, without using the array, whatever. But we see that we have a couple of variables we're going to need. We need a spacer width, a height, a bar width. That's really about it. So let's do some declarations. The spacer width is going to be, 10 pixels between bars, right? The height of it, in this case, let's just make it 100. The width of our bars, maybe 3 times our spacer, 30, something like that. We could play with those values as we needed to. When we actually run this to make an entire bar graph, the height is going to change each time, right? Or at least it could. But the spacer and the width probably ought to remain the same. Alrighty. Let's get this going. Let me go get my note card back up on the screen. So by draw spacer, I mean go forward that width, right? So let's try that. We're going to go forward Nope. Leo dot forward. You can abbreviate that to FD, which is useful because everybody always gets the R's wrong in forward, including me. The width of the spacer. And then we're going to turn left, and it's going to be a right turn, so it's 90 degrees. Leo dot left, 90 degrees. Now we're going to, so we've done these two. Now we're going to go up the height. So Leo dot forward height. We could have made it just HT to make it easier to type, right? Because height, another word that's annoying to spell. All right, and then turn right. Why am I typing turn right? Leo dot right, 90 degrees. So we've done that, and we need to go the width of the bar. So Leo dot forward the width, W-I-D-H. Maybe we should have just called them H and W, something like that. So we've done that one. Now I need to turn right. Leo dot right, 90 degrees. And now we need to go back down the screen the same distance that we went up the screen. So Leo dot forward height.
You have already FD.
Yes, thank you. That's a good reason for actually spelling out the words. I wouldn't have spotted that. All right. So I've done that. I need to turn left, and I need to draw my spacer again. So turn left, Leo dot left, 90 degrees, and then draw the spacer. Leo dot forward, the width of the spacer. Leo dot forward spacer. If I wanted to break them out to make them a little bit easier to spot, I don't know if it really would, but it would look kind of like that. I just added some returns. You don't need them. Left 90, forward height. Right 90, forward width. Right 90, forward height. Left 90, forward spacer. And let's see if it does anything. All right, there's our bar. And we would draw several of them. Now maybe we ought to relocate, you know, and go to the left edge of the window or something. Why don't we worry about that in a little bit? That'd be pretty easy, right? We just use one of those go-to commands to tell it to go to, you know, a specific position on the screen. Might also want to get rid of our little triangle, hide our turtle, because that makes it look kind of messy. But we have a start. This is our bar graph code right here. From there to there is all drawing one bar. So I'm going to put a little comment. Draw a bar. But we have this array full of numbers. We want to draw all of those, not just one. So we're going to need to put this in a loop, or it could be in a function. Let's say loop. So I highlighted all that stuff and I tabbed it over. You can tab either with the tab key, or you can go to Format, Indent, you know, or Control square brace if that's how you dig it, you know, whatever. Okay. So we're gonna use the same loop that we used to print out the asterisks, except obviously we're not going to print out asterisks, but it's going to be the same thing for v in nums. So after we create our turtle, for v in nums colon. Now the height needs to change each time, right? It's not always going to be 100. So why don't we say for height in nums? Well, that's kind of cool. Maybe the spacer needs to be smaller. What if we made a spacer of 0? You know, then they would all be mushed together. Maybe the width of the bars needs to be smaller. We should determine the width on the bars realistically by how many elements we have in our list. Maybe we should fill them in with a color. One thing we should certainly do is to go back this far, right? So that's 30, 60, 90, 120, 150, 180, 210, 240. Maybe we ought to go backwards 240 to start with. So before we actually start drawing, we kind of need to lift our pen so that we're not, or we could just use the go-to command, but we still need to lift our pen. And I always get the syntax for lifting the pen wrong, so lift pen, Python 3 turtle, Google that up. Hey, that looks cool. Is it just pin up and pin down? Yeah, it's pin up and pin down. Okay. Why do we do this? Because when we move to the left side of the screen, we don't want to leave our path. So, leo.pinup, pin spelled P-E-N, not P-I-N. And let's go back 240 pixels. So leo.back 240. We ought to make it better than 240, right? We ought to put that as a constant up at the top. And then put the pin back down. All right, that's kind of cool. But the width of each bar should be determined by the total number of elements, right? Because if we only have 10 elements on our screen, the bars are going to be wider. So at least on my screen, it seems like this is about 480 wide. My guess is it's actually 500 wide. So why don't we make a couple more changes, and then we're going to be done with this. Instead of 240, I am going to make that a constant. But let's make a variable called screen W for screen width is equal to 500. And we will use that for how far we want to go back, and then how wide we want to make each bar. So how far are we going to go back? Well, if the screen is 500 wide, we're going to go back 500 divided by 2. So where we had this 240, make it screen width divided by 2. And for the width of each bar, we're not going to hard code it to 30. We're going to hard code it to 500 divided by the length of the list. That's not taking spacers into account, but since we made the spacers 0, then this is going to be safe to do. In fact, we could delete the spacer command from here if we got rid of the idea of spacers altogether. I'm going to leave it. Someday we may want to make this more complicated. Okay, so the width of each bar is going to be the screen width divided by the length of our nums list, right? If we have 5 entries on our list, we want each bar to be 100 wide. If we have 50, we want each one to be 10 wide. All right, that's kind of cool. A bar down the bottom, a line all the way down the bottom, covering all of that might be good. If the bars were filled with a color, that might be good. The last thing that I want to do, though, oh, I'm really tempted to do that line covering the bottom. Let's do that. How are we going to handle that? I think I'm going to go forward half the screen width and then go backwards the full screen width, and then go back to the middle. That kind of makes sense to put a line underneath everything. And we ought to kind of speed it up because it's kind of getting boring watching it. But anyways, so I'm not going to lift the pin and lower the pin before I draw that line on the bottom. So I'm going to delete that part. In fact, I'm going to delete all three of these lines here. See Leo.pin up, Leo.back, Leo.pin down. Nuke those three lines. And let's just do Leo.forward, half the screen width. Screen W divided by 2. And then Leo.back the entire screen width because we got to there and now we want to bag them all the way over here. So just screen width. And then Leo.forward the screen width divided by 2. And that should put us back in our starting position. Okay, that was dumb. I did something wrong. I should not have done that forward command there, right? Because we draw a line here, and then we go all the way back here. I don't need to go back in the middle. So that command just needs to be deleted. That second Leo.forward. My mistake. Alrighty, spiffy. I like it. You know, we could spend all day making improvements. Like I said, filling each block, somehow labeling them so that we knew the height and what each one meant, right? Turning out the turtle at the end. But that's good enough. We have the idea of a bar graph. I think I'm going to change the width from 500 to a little bit smaller because we've kind of clipped our last one here. But then I'm going to call it done. I need to walk around and make sure that everybody's got it going on. So screen width 480. Maybe we could hide the turtle. I believe it's just Leo.hide. Maybe. I'm going to give that a shot. Not spend much more time on it if it doesn't work. Nope. Is it the whole word, hide turtle? Yep. That's cool. I don't need to see that triangle drawing everything. There's one variable that I could delete from our declarations up here because we redefine it here, right? Height. And there's another one that I could delete here because we redeclare it here. So to make it a little bit shorter, I'm going to delete those two variables from my declarations, the height and the width. Just help get everything on one screen, right? There we go. Final version. And I'm sure that I've gone too long with that. So just to clean up the code a little bit more, we're going to delete all references to the spacer since it's set to 0. It's not drawing anything anyways. Delete that line up at the top. Spacer is equal to 0 needs to go by. Forward spacer needs to go by. And the last forward spacer. I'm going to run it to make sure it still works. There are commands for changing the width of the window. If you wanted to make your window wider, you could do that. You showed it to your customer, I'm your customer, and I would make some suggestions. We're not going to actually implement any of the suggestions, but let's figure out what we might want them to be. They go, okay, that's a cute bar graph. But what else might we want to do to our bar graph? Open form. Great picture. It doesn't tell us all that much, or if it tells us a lot, it still could be made better.
Label it.
Yeah, labels would be of critical importance. Now, in this case, we don't even know what those numbers mean, but we could label the height, right? Because, you know, I don't know that that's a 15, whereas this is a 39. It's good for showing relative heights, but we ought to put some number on it saying, you know, how tall it really is. Another thing is we could scale it. What if all the numbers were very similar, right? All the numbers were between 1 and 10. You know, it's just kind of do that. Or worse, if all the numbers were fractions, like, you know, 0.1 and stuff like that, it looked like a straight line. So you'd need a scaling factor. scaling factor would let it fill up more of the screen. And if you were going to do that, you would want to shift it down so that it would fill up more of the screen. But we're not going to do that stuff. Maybe we'll add the scaling factor just for grids, right? So we're just going to need to multiply our height times the scaling factor. We want to scale them by 10 so that each block is 10 times taller. We'd multiply the height by 10 each time. I think that'd be too much, but maybe 4 would be adequate for the data that I chose. So I'm going to make one more declaration. Looks like we got rid of all of our declarations except that one, which is scale height, scale H is equal to 4. That looks weird, but scale H. I could spell out the entire word height. And so when we draw our height, when we get our height, let's multiply it by the scale. So height times equals scale height. And that should be the only change required to make that work. So I just added a line here. I put it above my draw barcode. I could have actually modified it here and here, but that would have made it, in my mind, a little bit harder to read. And what you would do to determine your scale is you would actually inspect your data, find the maximum value, and then base your scale based on that, right? Because if your maximum value is 1,000, you wouldn't want to be multiplying 1,000 by 4. You'd want to be dividing it by some value to get it to fit on screen. All right. And then colors would be nice, maybe letting the user pick the colors and all sorts of things like that. Users will ask for the world, and you have to kind of limit them unless, you have all the time in the world to make them happy, which is usually not the case. Okay, I'm pretty happy with this, and I want to start our lecture on files. D2L, PowerPoints. And this is going to be the last chapter we do this semester. And we have 2 more weeks after this, so probably not going to take 2 more weeks to lecture about files, so we're going to get a chance to explore a bunch of cool stuff. All right, file handling and applications. What is a computer file? It's a collection of data stored on permanent storage devices. The term permanent is important, right? Because if you just store your data in random access memory that kind of gets erased every time you turn your phone or your computer off or whatever, it's no good. Such as your computer's hard drive, a hard drive on the cloud, DVDs, USB drives, reels of magnetic tape. People have used all sorts of things, weird stuff for storage. They used to have what were known as drum drives, which was something the size of a washing machine. And it had magnetic stuff, in a cylinder, and the head moved up and down. It was a precursor to hard drives. It was easier to make that than it was to make a magnetic record player with the head moving on it. So you can have different kinds of files. Text files. The kind that you create with idle, that's a text file. You fire up Notepad, you type stuff in. That means that you can just double click on a file and it's readable text. Most files aren't text files, but the files that we use in this class are going to be text files. They're the easiest to create and read. What can you put them in? Numbers, names, any kind of text, right? Anything you could type on your keyboard. And then there are binary files. What's binary mean? Not that there's 2 kinds of it, but that it's stored as 1s and 0s, and it's up to the program to determine what those means. So pictures are binary data. Music is binary data. Word files and Excel files and stuff like that. Anything that you can't just, open with a notepad editor and see the data is a binary file, which is the vast majority, 99.9% of the stuff out in the world. So what do computer files have? We all kind of know this stuff, but a file name. They've all got a file name, and they've got other things too. If you're on a PC, on Windows, you can follow along. If you're using Mac or Linux, you probably already know how to do this stuff. But say I open a directory, and I do it in Windows, you may see this kind of look when you open your folder, which doesn't tell you a lot, right? It gives a cute little preview of it in the name, but there's more information to be had. On these Windows 7 machines, and there's different places if you brought your own laptop or whatever and you're using 8 or 10, you can pull down on this little thing that looks like a picture frame and choose a different view. Tiles, okay, tells us a little bit. It tells us the type of the tile and the size of the tile, or I'm calling it a tile, the file. Content, well, that's kind of cool. The one I always go to is details. Why? Because you get a set of columns that tell you all sorts of stuff, and if you want, you can add columns. You see where it says date modified? You could double click that and it would sort it by date, or actually just a single click. Right now it's showing my oldest files first, but if I click date modified again, the newest files first. So each file has an attribute that records when it was modified. How about when the file was created? That's useful information, but it's not being shown here. We can right-click on one of the headers. Date created is another one that can be shown. And it's kind of scrolled off to the side here. What if I think it's the most important thing other than the name? I could bring it over here and sort them by the date that the files were created. Now in this case, the date that they were created and the date that they were modified is just one and the same, right? Because I've been saving the files but never going back and changing them. But they might be two very different things, right? You saved a file, 4 years ago on your computer and you just went and edited it. Then the date created and the date modified would be two different things. So those are two different attributes. Now the attributes are not part of the file data, right? Just because I double clicked on a file doesn't mean, and it was a picture, right? It was a JPEG, a photograph. It's not going to go in and write into the photograph that I opened at a such and such date. There is a file table. They have different terms. Inside on your computer's hard drive that has both a link to the file and then the extra attributes, right? The date that it was modified, the type of the file, the size of the file, and stuff like that. It's up to the operating system to keep track of that stuff. But it's up to us to put some contents in the file and to give it a file name. And the file name consists of two different parts. Really, I think of it all as the same. But it's got the thing before the period is the name of the file, and the thing after it is the extension. And if you don't see the extension, and Windows doesn't do it by default, which is really lame, you can get it to show the extension. If you're using Windows 8 or 10, it's somewhere else. But if you go to Organize, Folder, and Search Options, and I think we did this towards the beginning of the semester, Folder and Search Options, and then you click on View, you can say, hide extensions for known file types. I don't want to hide my extensions. That's useful information. So I'm going to deselect that. Then there are other things. Display file size information and folder tips. Display the file icon. Always show the menus. I don't know what some of these do. I never change anything else other than that. Use select boxes to, where did that one go? Use check boxes to select items. Some people like that one. I never use it, but once you do that, then you get these little check boxes, and if you want to open multiple files at the same time, you can kind of do that. I never use that one, so I'm going to regret having chosen it. I'm going to go undo that change real fast. You saw me go to folder and view options or search and view options, go to view, find the options that you like or don't like and turn them off. Turn them on. All right, you see this bar up here? That shows the path of the folder that you are in. Right, so if you ever need to go and look for a file, and you know where it is on the, you found it in Windows itself, but you need to access it, via Word or something like that, you can go up there, highlight all that stuff, copy it, and then when you're inside Word and you want to open it, open. They sure have made this dialog harder to use. It used to be that when you did an open document, it immediately just dumped you to the hard drive, and you didn't have to choose OneDrive or this PC or browse or anything. Okay, so this PC, and then I could paste that into my file name, and it would show me all the files that were in that directory. Or I could come up here and paste it there, and it would take me to that directory. I'm using the terms directory and folder interchangeably. They're called a directory when you're talking about the disk drive structure, but people colloquially call them folders when you're talking about an application that views it, right? So, folders. These look like folders, right? So we call them folders. That's what Windows calls them. I think it's what everything calls it. And for those of y'all who grew up with, laptops in your cribs and stuff like that, you already know a lot of this just, instinctively. The file name identifies it. There are some rules for what you can call a file, and those rules differ based on the operating system. It used to be you couldn't put spaces in file names, but that's changed. You can't put slashes in your file names. Why? Because the computer uses slashes to indicate what directory it's stored in, right? If I'm looking up here, it's using those slashes to indicate the directories that it's stored in, so I couldn't use slashes in my file names. On Macs, it used to be that you couldn't use colons. That may still be the case, because it didn't use slashes, it used colons. I bet it's gone to using slashes to match the rest of the world, because Macs switched over around the year 2000 to being based on Unix, or a version of Unix, which is, old school operating system that DOS was also kind of based on, its appearance and stuff like that, and it certainly used slashes. So anyways, then we have the file name extension. That indicates the end of the file name that describes the type of the file. .txt, .dat, .docx. Now again, I'm going to mention on the Mac. On the Mac, didn't used to have file extensions, or if you had them, it ignored them. The application that would open the file was stored in that separate table. Remember I said that there was a file table? But it's nice to have extensions, right? Because if you send a file from your Mac to your PC, or from PC to Linux, or you email it to something, it doesn't copy that entire file table. All you get is the file name. And if it can determine which application to open just based on the file name, you're better off. So nowadays, all your personal computers use file extensions to dictate that. So that does dictate what kind of file, what application is launched when you double click on that file, but you can change it. Right, say I have TXT files, which I do somewhere. Text documents, right? Rich text documents. A rich text document is just kind of like a Word file, but it's more primitive, but you can still have font information and font size information and stuff like that, which you can't have with a text file, right? If I open up my Python script, I can't go and make some of the letters red and things like that. But you can do that with an editor. Every Windows machine comes with an editor installed called WordPad, which is a simplified version of Word. And it used to be that WordPad would only create rich text files, but now they create entire docs. So I'm looking for a text file. I'm not finding it, so I'm just going to sort by type. Find my text file. Okay, great. I've got some text files. When I double click on my text file, launches it in Notepad, which is also installed by default. But say I don't like that. I can come over here and do open with choose default program. And again, it's going to look a little bit different maybe on your Windows 8 or your Windows 10 computers. We're old school. We're kicking it with Windows 7 here. So what you do is then you pick which application you want to open your text files. Well, I like text files opening them in Word. I don't really. I'm going to change this back at a certain point. But then whenever I double click on a text file, it launches that application instead. So if you really wind up hating an application, but you have another application like photos, right? You have some JPEG files, and you don't like what happens when you double click on that JPEG file. It pulls up some lame editor. Or you downloaded a picture viewer, and now it's always launching that, but you don't like that picture viewer. You can go and you can change your default file type. I really think I've probably wiped out. Good thing I still have my original script. I'd paste it into a Word file. Try to keep it, but I still have my original script. Okay. And that information about which file is associated with it is based on the file name extension. Computer files have other things, other attributes. The size, right? File sizes are measured in bytes. But I really don't want to have to say that this file is 67,352 bytes long. I'd rather say, oh, that file is 65K. Or I don't want to say that it's 3,241,000. You're right. I'd rather say it was 3 megabytes or whatever. Roughly speaking, a kilobyte is 1,000 bytes. And a megabyte is 1,000,000 bytes, which is also 1,000 kilos. And if you've been to chemistry or physics classes, science classes, or whatever, you'll recognize that, right? Or if you're a drug dealer, you know, I have 12 kilos of, you know, whatever. So, you know, and then a gigabyte is 1,000,000,000 bytes, but it's also 1,000 megabytes. And a terabyte is 1,000 gigabytes. So if you're old enough to have bought hard drives, you know, back in the 90s, it may have been measured in megabytes. And then in the 2000, your hard drives are measured in gigabytes. And nowadays, you can buy external drives that are terabytes. And you can just bet that large companies like Google, you know, that have all the information in the world, and Facebook or whatever, have drive sizes or, you know, conglomerations of drives that are far beyond terabytes, petabytes, or whatever, you know. You can see it goes up by 1,000 every time, right? Now, where scientists and computer people differ is that in science, it's an exact 1,000. A kilo is an exact 1,000, and a mega is a exact million, and a giga is an exact billion. But in computerese, a kilo is 1,024. Why is that? They're weird. Well, it's because that's a base 2 base number. And a megabyte is 1,024 kilos. And a giga is 1,024 megabytes. And a terabyte is 1,000. Okay, where'd that 1,024 come from? Let's put on our thinking caps back to our binary days when we had 0, 0, 0, 0, you know, 0, 0, 0, 0, whatever. You know, that was the ones place. That was the twos place. That was the fours place. The 8, the 16, the 32, the 64, the 128. So, if you have 8 bits there, you have 256 different values that can be stored there, which is why languages on computers used to be stored in 8-bit values, right? Because you could put all the English letters in there, and you could throw in some punctuation, and, you know, then you could have some special graphic symbols. If you're using a PC with a numeric keypad, you can hold the Alt key down and type something on the numeric keypad, and you can get those weird ASCII values, like 100 is a lowercase d, 101 is a lowercase e. All right, that's great, but 150, ooh, 160. They get even weirder as you go up. That was a 190, 200, 220, 221. Yeah, right. And so if you used programs way back when that were all character based, they probably drew nice boxes around the you know, the data, you know, using symbols like that. So ASCII was 8 bits wide, but it wasn't. That's not large enough to hold every character for every language on the planet, right? By far not. And it used to be that you would view a web page and it would look like garbage, and then you'd have to switch the mode. Oh, that's not English ASCII. This is Russian. and you'd switch the mode to Russian, and it would view it in Russian, or you'd switch the mode to German, and it would view in German. That's back in the 90s or whatever. So then computer scientists came up with something called Unicode, which is a multi-byte character set. For example, what if we had 16 bits rather than 8? We could hold a lot more characters in it. Let's just keep doubling. 9 could get you up to 512, different possibilities. 10 bits could get you up to 1024. And via the miracle of doubling, these numbers start getting really large really quickly. All right, I'm starting to lose count here, so I'm going to start making up numbers. Right, these aren't precise. I do happen to know the next one. 16 for some reason is burned in my brain. Okay, like that. Okay, so by the time you get to 16 bits, you can hold up to 35,000 different values in it. 35,000 characters. Pretty good swath of the human languages could be stored in that many characters. And then people started using the, emoji and stuff like that. And so each time an emoji is universally accepted, it has to be added to Unicode so that, all the operating systems will be able to display your brand new upside down smiley face and stuff like that. So anyways, Unicode tends to use 16 bits to store its data. Your Nintendo probably displayed graphics with a color palette of 256 colors, right? The graphics weren't real good. And not only that, it had a limited number of pixels on the screen. And then you bought your Genesis or your Super Nintendo and it used 16-bit graphics. So the pixels on it could be one of 36,000 different, colors on it. And then your PlayStations came along and they had 64-bit graphics or something like that, millions upon millions of colors. You can see that these numbers are getting very large very quickly, right? Now, I'm not going to keep doubling them. But how much data could you store in 32 bits? These numbers are also important in terms of, I had an 8-bit computer, which meant that it can only access 256 kilobytes. I had a 16-bit computer, which meant that it could only access, that many kilobytes, which would be, 35 megabytes or something. And then we got our 32-bit computers. And you may know that when you install Windows or programs, you have to pick between 32 and 64 bit. The equation for figuring out the number of values is 2 to the power of the number of bits. So 2 to the power of 16 is 65536. I did something wrong there when I was doing my doubling. Oh, 32 doubled is not 35,000, right? It's 65,000. Which people round up to 64, right? That's 64K. Probably really is 64 times 1024. And then 32. 2 to the power of 32. That's 4 billion. 4 gigs. Huge difference between 16 and 32. So when chips made the leap from being 16-bit processors to 32-bit processors, they could address a whole bunch more RAM. How about our 64-bit computers? The highest that we've got nowadays. That's probably not true, but the highest that people buy, right? You install 64-bit applications or 32-bit applications. We're not buying supercomputers for NASA or anything. So let's do 2 to the power of 64. It's a huge number. It's incomprehensibly large. So if we were going to measure that in gigabytes, we could divide it by 1 billion. Divide by 1, 2, 3, 4, 5, 6, 7, 8, 9. That's still an impossibly huge number. So 64 could address that many gigabytes. So it wasn't that long ago that the most memory you can install on your laptop or something was 4 gigs. And if you installed something larger than 4 gigabytes of RAM on your computer, it had to do something really special to access it. Now that you have your 64-bit processors, you know, it's going to be a long time, I think, before we start maxing out, you know, installing that much RAM in your computer would take like a truck, you know, to hold it off. So anyways, that is why things migrated from 32-bit to 64-bit, you know, sometime in the 2000s, because 4 gigabytes wasn't large enough anymore. All right, so why did I go off on that diversion? That's a really good question. Let's go back and look at the slide and remind me. Oh, because of this slide. Just remember it goes up by 1,000 each time. This is a slide showing file names, a picture of a baby. That's very generic. I would be very suspicious. I wouldn't click on a file that said it was a picture of a baby. That's too generic. Okay. And then a date. That's probably the date created or the date modified. It doesn't say. The file type, the size, stuff like that. I like how blurry that picture is. All righty. Organizing files. Directories and folders. In olden days, you didn't have folders or directories, right? You stuck a floppy disk in your computer and all the files were just right there, right? You did a listing of them, didn't have folders. But that's kind of a lousy way to store things, right? If you have, you know, hundreds of thousands of files on your computers and they were just all in one level, that'd be impossible to navigate. You know, that was great when you only had 10 or 100 files on a disk, but nowadays our disk drives are so huge that would be really lame. So directories and folders. And those directories and folders do not correspond with certain parts of your disk, unlike a filing cabinet, right? It's not like this part of the disk has my, you know, documents and this one has my application. Those are virtual folders managed by that file table that I told you about that the operating system has to keep track of. And if you've ever had a hard drive completely crash and you had to use some kind of file recovery software, when you were pulling the files back in, it may have lost its directory structure, which makes it really hard to recover the specific file that you were looking for. And so the path, pardon me, okay, the path is the folder, the directory, plus the name. Some people call that a fully qualified path. I believe another abbreviation for that, I could be mistaken, is UNC. What does UNC stand for? Yeah, right. Okay. File path. Uniform naming convention. What is a uniform naming convention? Well, you know, nowadays you don't just have things on your own computer. You have things on those servers and stuff like that. And so the path can involve a server name, just like drive letters, right? We might have C:\/ as our path if you're accessing on the, you know, on the network. You might have a server name. Pop open the command prompt. Either go to the start menu and type in CMD, or if you hit the Windows key and R, you can type in CMD. And then type this command in, net use. It shows you all your current drive letters, network drive letters, not local drives, hard drives and stuff like that. And so supposedly I have access to these drives. I never use them, but I could go out and I can see what's on my R drive. You might be curious to go out on your X drive. I don't know if students have a place where they could store files, you know, for themselves. MD, that stands for make directory. MD, test, nope. Why do I have a directory if I can't store anything in it? Anyways, okay, so this is the server path to that directory, right, to that file. You can see that it's kind of doing some magic where we have a server and then we have a folder name on that, but it's mapping that to a drive letter on our computer. And maybe you've seen that before. There's a way to go into the Windows configuration and you can say, okay, I want this server to be drive letter F, this server to be drive letter G. You know, if you've done a lot of configuration of servers and, you know, if you're a network admin or you're a guru, you probably have done that kind of stuff. So UNC, Universal Naming Convention. That is even a more sophisticated version of a fully qualified path because a UNC can have a server name there instead of a drive letter. So the data hierarchy. right? If we type into a computer on our keyboard, we're generating characters. But when we're filling out data, right, you know, I'm going to fill out my address or something like that. We're filling in fields, my name, my address, my phone number. So a field is a collection of characters. And this is actually talking about databases in particular. But, you know, pretty much a lot of what we do involves databases behind the scenes. Like, you know, you're buying something from Amazon or booking a flight or whatever. And then a record is a group of fields that go together, that are collected logically together. A file is a group of related records, and a database is a group of files. Again, that's simplified, and some of y'all are going to go on to take, you know, database courses, and you'll learn more specific definitions. But, you know, so I have characters, which are bytes or multi-bytes if they're Unicode. And then I have fields, fiends, I hope I don't have fiends, fields made of characters. I have records made of fields. I have files made of records. And then I have databases made of files. And again, this is a database-specific view of the world. Right, your photographs and stuff like that do not correspond to this, right, because they're binary data. They do sort of have fields in them, though. A photograph, I think I've mentioned this. If you take a picture with your camera or your smartphone, it stamps it with your, you know, your GPS coordinates and the name of the device that you took it in, you know, and the resolution and stuff like that. So if you mail somebody, you know, a JPEG or something like that, you may be mailing them, you know, coordinates to your house or something. You can find applications that'll remove that. If you upload it to Facebook or something, it strips that identifying information out. If you take a screenshot of your picture before you mail it and then you send them your screenshot rather than the original picture, then, you know, the screenshot doesn't have your address and stuff like that in it. Just kind of a little privacy tip there. So what if I was writing an application that created a mailing address? So my fields, my name, my address, my country, my zip code. Maybe that's enough, right? And then I would have a file. Excuse me, the record would consist of those fields. The file would consist of multiple records. The database would consist of multiple files so that you could relate them together. Why would you want to relate them together? What you might have a database, you know, which is of addresses. I said database, a file of addresses, and then you have a file of purchases. Those are separate things, right? And then you probably need something that ties those things together, right? So that you know that these purchases went to this address and these purchases went to this address. And it's up to your database to manage all that. This is just showing that. Here I have some fields. My name, whatever that number is, and then a year, and then some yes fields, and then what state I'm in. I have no idea what these Y's and these N's and that number is supposed to represent, but we can kind of figure it out. So the record consists of all that information. Each record is composed of multiple fields, and those fields are composed of characters. The file contains many records. All right. We're almost running out of time for today's lecture, but I do want to modify our program to write some data out. So, you have effectively two operations you can do on a file, right? You can read from it, you can write to it. We're going to write some code that writes to a file. We're going to go back and modify our script to write to the file. Where's my script? There we go. Remember when we were doing our, our days of the week and then our hours, so we had two different arrays. Days is equal to, and it had something like this. Monday, Tuesday, Wednesday, and I had more than that, right? But I don't want to take forever filling in all this time. 4 days a week is enough. And then we had the hours worked each day. You know, Monday I worked 10 hours. Tuesday I worked 5 hours. Wednesday I was sick, I didn't show up at all. Thursday I made up for it by working another 10 hours. That's today's economy for you, 10 hours a weekday. All right. Anyways, let's write this out to a file. Let's ask the user for a file name. File name is equal to input. Save to what file? Question mark. Now we have a file name, we can open our file. File is equal to open, parentheses, file name, comma, and we want to open it for writing, so we're going to put quote W, end quote, end parentheses. Guess what you'd put there if you're opening it for reading? R. And this is specific to this language, but you know, all languages are going to have some variant, you know, of that because of same concepts. Alrighty, now let's iterate through our loop, but we're not going to print our data. We're going to write it to a file. So for I in range up to the length of one of the lists. So I in range, parentheses, len, parentheses, doesn't matter which one, they're parallel, days, colon, file.write, let's write out the day that it is, plus a comma. Now that's a plus and not a comma, right? This is a plus sign here. It's not the print command where we separated everything with commas. Plus, and I'm messing that up. It wasn't days. Excuse me, it wasn't day. Our array name was days. Maybe I'm going to separate this in multiple lines. So days, subscript I, in parentheses, and then do another file write. File write, just a comma out. That comma is known as a delimiter, and you can have different kinds of delimiters. What does delimiter mean? It means it divides the data so that when an application loads this file, it knows, you know, where your name ends and your address begins. A comma is not a good delimiter, by the way, because your name may have a comma in it and your address will have commas and stuff like that. But for our purposes, it'll work great. Now let's write out the hours that we worked that day. Hours, subscript I. And then we want to write out an end of line character, right? So that all of our data is not just on one line in the file. The print statement does that automatically, but the file.write does not. So file.write, quote, \n. The backslash is the one above the enter key, not the one below the question mark. And let's close our file. File.close. And let's tell the user what we did. Print data saved to, end quote, file name. Really hope I started a recorder for all this. Okay, good. And then run it. We ought to increase the speed of our turtle so that we don't have to wait for the right above our for loop, way up here, for height and num. Let's do turtle.speed 0 to max the turtle speed out. Right. That's just for our convenience. You don't have to do that, but add turtle.speed 0 up above your for loop in your turtle code, then come back down here and finish typing this and run it. I can't say that it's making much difference. Also thought that I turned off the, I guess I turned off the turtle after I drew that bottom line. But anyways, okay, save to what file? Let's just call it hours.txt. Something.txt, whatever you want to call it. Heck, we could give it today's date. April 26.txt. I'm stuck in the past. April 26.txt. And it blew up. The right argument must be string, not int. And I knew that and I forgot. This wasn't one of those intentional mistakes that I'm trying to show you. You know. Okay, the problem is that's a number, right? It's not a string. And that's a number, it's not a string. So you see those two things there? We need to add, just like we convert data to a float or an int, we can convert data to a string like this. str parentheses, and then tack on another closed parentheses on the end. So I had to fix this line. Put that string command there. I'm also going to have to do the same thing for the hours. So come over here in front of the word hours, do str, open parentheses, and at the end of the whole thing, put a closed parentheses, because you always have to have, match number of parentheses. Why did that speed not work? Because I called it turtle.speed, but what's the name of our turtle? Leo. So if you cared about that speed, make it leo.speed. Alrighty. I'm surprised I didn't generate a syntax there. Alright, much better. Alright, save to what file name? April26.txt. It's going to overwrite the last file I made, except it didn't actually finish making the file, did it? And then it says file saved to April26.txt. Now if you close everything and you go and open your directory where your source code is, you'll also see that new file. So I'm going to go to my directory where my source code is, where I saved it. Why can't I find it? Scripts. And I sort by date modified or date created, and there's my data file that I just created. And if I open it up, there's my data, right? I could write a program to load that file, and then draw a bar graph of it or something like that, whatever I wanted to. Saving files and then loading files is how programs are kind of linked together, right? Conceptually, although, one file is probably saving it to a database and the other computer may, be located on the internet, loading it up that way. But anyways, so we have created our first file, I believe, unless we did this previously, and I don't think we did. So on Tuesday, we're going to create more complicated files, the kind of files that we could import into Excel, and draw pretty graphs or, perform complex calculations with there. And we'll also write programs that read from the files that we make. But that's enough for now. Let me make the Dropbox, and I know that some people have syntax errors, but some people don't and would like the Dropbox. Go ahead and give me the txt file and your py script. Alright guys, the Dropbox is folder R. Dropbox R. Give me your py script and your txt. I'll stop the recorder, put the code back on screen, and anybody who doesn't have it working and wants to get it working, we'll do that.